Okay, and we're back, and hopefully with a better image now. Sorry for the delay. Let's take a look from here as to what's going on. So why do we mess with geometric series? Well, the reason is we can actually do a lot of things with it. For example, we can start writing things as ratios of integers. So if you have 0.8 with this bar over the top, that means repeating, you can write this as 0.888888, so on and so forth, right? And what actually happens is this equals 8 over 10 plus 8 over 100, or 10 squared, plus 8 over 10 cubed, plus yada yada yada. Okay, so at the end of the day, what does this equal? Well, this equals the summation, and equals 1 to infinity of, well, this would be 8 over 10 to the n, which we luckily know is the summation n equals 1 to infinity. We can write that as 8 over 10 times 10 to the n minus 1, which allows us to use our geometric series. So in this case, we can pull the 8 tenths out in front, so you get 8 over 10 times the summation, n equals 1 to infinity of, well, this will be 1/10 raised to the n minus 1. So that means a equals 8 tenths and r equals just good old 1/10. So you have this whole thing becomes, 8 over 10 over 1 minus 1/10. And now we can take that 10 on down and see what happens. So this should become just 8, and then we have 10 times 1 minus 1/10, which is 10 minus 1, so this becomes 8 over 9, which is what you might already have known. But what can happen is we can expand this to others, and so for example, this 0.516 repeating, that's 0 point, and notice we have 516, 516, 516, and we can continue that process forever and ever. But writing this one might be a little bit more difficult. So instead of 5 over 10 and then 1 over 10 squared and 6 over 10 cubed, we won't be able to find a pattern. So an easier way for us to write that is 516 over 1000 to start. And then, so that takes care of those first 516 values. And then next pair, well, that'll be 516 over, well, how many digits are we? Well, you got to have an extra 3 zeros to that. So another way we could put that is just 1000 squared. And then another 516 over 1000 cubed. Plus yada yada yada, and you keep on going. So now looking forward from here, you have that this equals the summation n equals 1 to infinity of, well, this is 516 over 1000 to the n. Okay. And so moving forward from here, where do we go? Well, this will give us another way to write it is just pull out the 516, pull out the 1000. So 516 over 1000 times that summation, n equals 1 to infinity of 1 over 1000 raised to the n minus 1 power. Okay, so moving forward, this becomes, we have the 516 over 1000 up in the numerator, and then we have 1 minus 1 over 1000. This allows us to drop the 1000 down, so notice this becomes 516, and then we have 1000 minus 1, which is 516 over 999. And now we're writing things as fractions. So there's some beautiful results that we get from this. So, and hopefully that makes sense in terms of why we care about these geometric series. If not, let me know. I'm here to help. That's the main purpose of this. So now we want to get to something real good. So we have a summation n equals 0 to infinity of this e to the n c equals 10, and we want to find what c is. How the heck do we go about doing that? Well, this requires a little bit of work, but not much. So c is just some constant. N is the variable, and you can see that by its index down here. So that's your n value right there. So this can be rewritten as e to the c, which is just some constant raised to the nth power, and we want that to equal 10. So at the end of the day, what happens? Well, if this were to work out, we need it's e to the c is just some constant, so that's a geometric series. So this becomes, and notice we have n equals 0 to start, so we're in good shape in that case. You get 1 over, whoops, sorry, didn't mean to do that. 1 over 1 minus e to the c equals 10. And so now where do we go from here? Well, multiply both sides by that 1 minus e to the c, so you get 1 equals 10 times 1 minus e, oops, that should be an e to the c. And so distribute that 10, so we get 1 equals 10 minus 10 e to the c. Move that 10 on over, and notice we have now negative 9 equals negative 10 e to the cth power. Divide both sides by negative 10, and then you get 9 over 10 because the negatives cancel, equals e to the c. So how do we solve for this? Well, we take a natural log of both sides, and so you get natural log of 9/10 equals natural log of e to the c. And the natural log and e, they kind of go away and leave you with what c is. So you get c equals natural log of 9/10. Okay, questions on that? Alright, if I don't see any questions, we'll move forward. And into integral tests. So what does an integral test look like? Well, in terms of what we have, we need a continuous positive decreasing function. So there's three parts. We need continuous, positive, and decreasing function on an interval. Now we write 1 to infinity because usually that's what our summations are, but if it's not 1 to infinity, just adjust to whatever your index starts at. So we need, that's where we'll need the continuity, positive, and decreasing. And where an equals f of n, right? So usually what we'll write though is we'll write f in terms of f of x dx, but you can write it as f of n dn. There's no difference there. And where this all stems from, to kind of show you, it's kind of the idea of a comparison theorem. So let's say we had a curve, and I'll actually draw this. In order for it to be convergent, obviously, even in cases where it's divergent, when we're looking at series, we're seeing how fast these sums go to 0. Do they go fast enough to where things actually go to a number? So let's say we have something like this. Okay. Say this is our function. And what's happening here? Well, in the big scheme of things, we can use a right endpoint approximation, and notice, so we get something like this. And I can pretend the curve goes up wherever we need it to. But so if this is 1, this is 2, this is 3, this is 4, 5, and 6. So since I have positive decreasing, that's actually important here. What can we say? Well, this value would be a1. This value right here would be a2. This value right here would be a3. This value corresponding to right there would be, and I'll have to draw it on over, that's a4, and so on and so forth. Each value, notice we're getting closer and closer to 0 on the y-axis, but what happens is the sum of all these areas, notice our rectangles all have length 1, so the sum of the rectangles areas would equal a1 plus a2 plus a3 plus so on and so forth. So if this integral converges, what would that mean? Well, that means that the sum of all the rectangles converge, because we have something that you're always adding a positive number and it's bounded above, but this thing is bounded above and it's increasing towards that number, and so you can actually get the values in terms of a good approximation. So that's the reason the convergent works. For the divergent, notice in this case we used the right endpoint. Oh, actually we were going 1 to infinity, so well, yeah, same song and dance. We were using the right endpoint if it was from 0 to infinity, so I was kind of working with that. You can do the left endpoint, and then you can kind of see the same thing. Your rectangles in that case would be if we were going from 0 to infinity, so if I extended it over here, but I'll just start at 1. I can also go this direction with rectangles, right? And notice that would be if I have something diverging for the integral, I have something larger that diverges, and this should all be the same sums going on there. So we can play the same game just going the opposite direction. That's the beautiful part, but we do need positive and decreasing along with it being continuous. If we don't have continuity or any of those, all things fall apart, so keep that in mind. Now, I will kind of, in order to save some time, well, actually we can go through it, it's not too bad. I was going to say to save some time we could end up cutting down and just not show that it's positive and decreasing. The positive part's easy actually in all these cases. Notice we start at n equals 1 and we have two positive numbers, so this thing's positive, and we have, so first off, f of x in this case would equal x squared e to the negative x cubed. And for x greater than 1, and why am I choosing 1? Well, it's because that's where we're starting our interval. F of x is greater than 0, so that means it's positive, right? Nothing really to look at there. Now, how do we show it's decreasing? Well, that's pretty easy in terms of derivatives, right? If the derivative is negative for all values on the interval, we're in good shape. And in this case, it's going to be the same song and dance that we're hoping for here. So we got to use the product rule. And so you get 2x e to the negative x cubed. And then after that we have plus, so this would be x squared, and the derivative will be negative 3x squared. And then we have e to the negative x cubed. Okay, so this might be hard to see if it's decreasing on that interval. But if you look, we can simplify this a little bit. You can factor out an e to the negative x cubed. And then you're left with 2x, and then this will be minus 3x to the 4th. So if you factor out an x, you get x e to the negative x cubed, and then we'll have 2 minus 3 x cubed. So now think about this. These two terms are positive when x is greater than 1. Okay? What's going to happen when you plug any number in for x greater than 1? Well, that whole thing is going to be negative. And since that's negative, that means this function is decreasing. So this is negative for all x greater than 1. So this function is decreasing on the interval 1 to infinity. Okay, does that make sense on that part? So without seeing any questions, I'm going to assume that we're good on that part. So now what I'll do, just to save room, I'm going to erase that piece, but that's actually a very important piece. Make sure you have continuity is pretty straightforward. You have a function, you don't have any, there's no points where e to the negative x cubed, you'll get 0 in the denominator or anything like that, so you're in good shape there, especially on 1 to infinity. So didn't have to worry about that. Just show it's positive, show it's decreasing. Positive shouldn't even be a problem. If you don't see a negative value in there, then it's we're good to go. So okay, So you said, I know you just worked it out. I see Chelsea asked a question. I know you just worked it out, but I was wondering if you could say what thought process when looking at these problems. Okay, so the thought process on this is it's going to help if you can recognize antiderivatives real quick. I'll be honest with you, we're going to learn actually a quicker method later on down the road, especially when we get to ratio and root test. And I'm not going to cover ratio and root test today unless you really want to see that. I was planning on holding a second session later on this week, and I can iron out the kinks of the tech issues that I was having this time too. So I was planning on getting through alternating series test, and that'll be a little bit easier. But the thing you can recognize real quick on this, if I take the antiderivative of x squared e to the negative x cubed, that's going to be a u substitution with u equal to negative x cubed, and then it'll be negative 3x squared, but we can still take care of that x squared. So that seems like an easier antiderivative, and that's why we'd use an integral test. So hopefully that makes sense in terms of why use an integral test, because I think that's a great question, and the more tests we get, it's going to be, well, what the heck do we use in these cases, right? But so the fact that this was an easy antiderivative, and the same thing with the next one, and I say easy, it might be somewhat challenging at first, but you get more and more the hang of it the more you practice them. So if we can set this up and do some similar integral, we're going to be in pretty good shape. So that's what we're gunning for, is can we recognize one of those cases. I will be honest though, the ratio and root test will handle a lot of these. There will be cases when you have to use integral test or alternating series test or comparison test or limit comparison test, and there are unique cases that it happens over and over again. But the ratio and root test will take care of a ton of these. Actually, I'd have to double check on if it takes care of this one. It might not. We can go through that when we come to it, and actually I'll go back and I might even toss it back in just for a good refresher. So, but hopefully that makes sense in terms. If not, please let me know. I'm glad to have you asking the question. That's the main part of what I'm looking for, is what's going on with these pieces here. So is it okay if I erase this section right in here to give some more room to finish off the problem? Just let me know. If not, I can always reproduce that too. But hopefully you see that it's decreasing. That's actually important. There will be cases if it's not decreasing, there's actually something you can use in that case, and it's called the test for divergence. That basically says if our limit isn't going to 0, so if these infinite sums aren't going to 0, you're going to be adding an infinite number all the time. So this thing would never converge in those cases. But since it's going to 0, we'd have to do more of a check. So now we have our function. Oh, I should have left the f of x there. So f of x equals x squared e to the negative x cubed. Okay. And so now moving forward from here, well, we can set up an integral from 1 to infinity of f of x, basically, so x squared e to the negative x cubed. And we know that this is an improper integral, so we do that limit as t approaches infinity business. And we have the integral from 1 to t of x squared e to the negative x cubed. And I mentioned this isn't too bad of an integral, so I better put my money where my mouth is, right? So if we have x squared e to the negative x cubed, I'm actually going to take the indefinite integral, just so we can kind of see what happens here. And then I'll plug it back in a second. If you let u equal negative x cubed, then notice you get du, as I mentioned before, equals negative 3x squared dx. And so we have an x squared, we have a dx, we just don't have that negative 3, so that's a simple fix. We go du over negative 3 equals x squared dx. Now if you don't like that method for finding antiderivatives using u substitution, let me know. I can go through it another way where we actually divide by the whole negative 3x squared and just cancel things out as well. But so this leaves us with e to the u, and then we have du over negative 3. Right, so you can pull that out in front, and so notice this is negative 1/3 e to the u, which is the same thing, and plus a c. I'm not going to write that for right now because I'm plugging it back into something with bounds. So this is negative 1/3 e to the negative x cubed, and plus, that's where I'll put the plus c. Okay. Or I'll put c minus just to be kind of fancy there, I guess. Alright, so this thing becomes the limit as t approaches infinity. And what do we have? We have negative 1/3 e to the negative x cubed evaluated at 1 and t. And plugging that in, we get the limit as t approaches infinity. Now, just to write this a little bit nicer, I'm going to put that e to the negative x cubed down in the denominator where it belongs. So this goes negative 1 over 3e to the t cubed. Then minus a minus, that'll make a plus. And so you get, plug in 1, so you get 1 over 3e to the 1 cubed. Well, notice this whole thing, let me circle that there. As t goes to infinity, this whole thing goes to 0. So this equals 1 over 3e, right? But so now, this doesn't mean that the summation, this whole series equals that. What it means is that it's bounded by 1 over 3e. It's a upper bound. And what we can say now, and here's the big thing, we want to start writing these things out. So sum of n equals 1 to infinity of n squared e to the negative n cubed converges. And now we're going to start writing these tests by the integral test. And we have our work there. Okay? Any questions on that one? Please let me know if so. That's what I'm here for. That's the main part of me being here. So I want to make sure we get this stuff down in terms of what's going on. So basically, all we're looking at when we see these, do we recognize this is going to be something we can find a good antiderivative for? And if so, let's evaluate that antiderivative, assuming one other assumption there, that this function is positive and decreasing. All right. So in the next case, notice actually this one's going to be easier for our limit n going to infinity being 0. So it's kind of giving you an idea we're probably going to be decreasing. I'll illustrate that again on this one. So if we go f of x equals, in our second case, 1 over x natural log of x. So I'll do that extra step. F prime of x. Well, this is raised to the negative 1 power. So you can write it, maybe this might look a little better. X ln x to the negative 1. So that means this is negative x ln x to the negative 2 times the derivative of the inside. Now this is going to be a little bit more interesting, but that's natural log of x plus, well, x times 1 over x, right? So notice, oh, and I should have said the first thing is greater than 0 for x greater than 2. And notice the reason we're using 2 in this case because we start at n equals 2. So in this case, though, we have negative, and then all this stuff goes up top. This is natural log of x plus 1. And down below, we'll have x ln x, the quantity squared. Well, notice, if this thing, we have 2 up here. Natural log of 2 might not be something you recognize real quick, but no need to worry about it. With all those, it's not going to be any bigger than 1 or anything like that. But we're in good shape. It's not as big as 1, but it's still some positive number is the main thing. So, and then down below we're going to have a positive number. So you have a positive over positive with a negative symbol out in front. So this is decreasing for x greater than, well, actually all we need is x greater than 2. Just to illustrate it a little bit more, some people might not believe that. So the way I can find that, just to kind of illustrate it, make sure we have this down. If I set this thing equal to 0, so notice I get natural log of x plus 1. So we get natural log of x equals negative 1. So the way to get rid of this is you raise both sides to the e power. So you get x equals e to the negative 1. So you'll have somewhere on here is e to the negative 1, right? If I do e to the negative 2 and plug it in here, I get a negative up top now. and the negative and a negative makes a positive. So if this is your x value, this is your f prime of x. Notice you have a 0 right here. You go from positive to negative. That's why it's decreasing. E to the negative 1 is actually the cutoff point, and I should have illustrated this a little bit more thoroughly before. But for x greater than e to the negative 1, which is, well, what that means is x is greater than 2, it will definitely hold. So hopefully you see we are using Calc 1 quite a bit there, and hopefully that's the quicker part, right? But so now that you have all this, hopefully that makes sense on the part about this function being decreasing and being positive. And continuous, we're 2 and higher, so that you don't have any values where, so it would be undefined when n equals 0 and n equals 1, but those aren't in our values that we have to worry about. So I'm going to erase this part and try and tackle the integral now that we have it's decreasing. Let's see if we can do the integral test part. So moving forward from here, it all goes back to integration. And if you remember improper integrals, pretty much everything that happened in improper integrals just happens again in series. So we're going to do the comparison test next and see how that goes. So moving forward on this part, we can write, we have f of x equals 1 over x. ln x is the associated function in terms of x. Our integral, though, would be from 2 to infinity. Can anyone tell me why it's 2? Why didn't we start this thing at 1? And just setting this thing up, I'll change the infinity to a limit as t approaches infinity. Yeah, that's exactly right. So Chelsea, you'll get a bonus point. Just shoot me an email on that. It is the index. So it's the index that gives us that. So since our index is 2, right there, that's why we keep our bottom bound at 2. We're basically matching the bounds on the summation there, or the series, whatever you want to call it. So we have this. Now, I'll do the, once again, I think the antiderivative worked well last time, so if it ain't broke, don't fix it. If we have 1 over x ln x dx. U substitution, right? So what will we call u in this case? I'll have you all take a guess on this one. So you have quite a few choices. What do we think is u? U equals 1 over x is a good guess, okay? So let's check out what happens though, right? If we go u equals 1 over x, right? Then we get du equals negative 1 over x squared dx, right? So if that happens, notice we can't account for that piece in natural log x, right? So that's good. We got a good idea. So didn't quite work out, but it's a gosh darn good idea. So let's see, maybe we can improve upon our u choice, right? So we can get that natural log of x involved. So any other ideas for what u is? And this is exactly what we'll encounter sometimes. Yeah, it is ugly. So yeah, your substitution will get, we could actually, you know what, I mean, to be honest, we could work with it, but we'd have to do a lot of finessing in that case if we did u equals 1 over x. A lot of algebra involved in terms of trying to get that, and I'm not 100% sure we'll be able to do it perfectly. Yeah, so if you did x equals 1 over, or so u equals 1 over x, we might be able to take it there. The thing is, we would need to handle that du. We basically make this integral more complicated and have to use integration by parts. So you get du equals negative 1 over x squared, right, dx. In order to account for that, we'd have to all of a sudden figure out, okay, how do we get this negative 1 over x squared? Well, that would be, we've got to cancel that out, so we get negative u squared would equal negative 1 over x squared. So that would cancel that part out. Now we also have to solve for natural log of x. So how the heck do we do that? Well, notice you get x equals 1 over u, and so then you get natural log of x equals natural log of 1 over u. And so that would be our new integral. So it's going to be nastier, and then we'd have to do another substitution to go there. So I see the new one, and that is beautiful. And Dimitri, shoot me an email. You'll get a bonus point for getting it now. So u equals natural log of x. That's a great choice. This one will work out nicely. So you get du equals 1 over x dx. So I got to make sure I'm not running out of room here too. So if keeping that in mind, what do we get? Well, our new integral becomes, well, we already have the 1 over x dx. That's sitting right there, so that's just du. So this thing, whole thing becomes just 1 over u du. And yeah. Well, you say you had only two choices. I like how you think that, but sometimes there can be extra. So sometimes the substitution might not be anything that's sitting right there in terms of the two values. So there can actually be other cases where there's other choices. Actually, to give you a real quick integral, say I gave you x over x to the fourth plus 1 dx. In this case, you might say, okay, I either have x to the fourth plus 1 or x being my substitutions, and neither one will work. In fact, if you want to start to check yourself, this one's going to be, I think it's 1/2 arctangent of x squared plus a constant c. So that's one where you have to let u be equal to x squared, and you have more than those choices. So it's a u substitution problem, but it's a lot different. So it's not always as simple as we say. It does take a lot of practice on a lot of these, and so give yourself some credit. I mean, finding that choice, it's not 1 or 2 all the time, so keep that in mind. So our answer here, what does this become? Well, this is just natural log of the absolute value of u plus some constant c. That's natural log of, well, u was natural log of x, so natural log of x, and plus that constant c. Okay. So now, where can we go from here? Well, we have our integral. Oops, I don't need that anymore. This whole thing equals the limit as t approaches infinity of, well, it goes natural log of x and evaluated at 2 and t. So this is the limit as t approaches infinity of the natural log of t plus, or not plus, my apologies, minus the natural log of 2. By the way, when you take a log of a log, things slow down drastically, so keep that in mind. But even with them slowing down, as t goes to infinity, this whole thing equals infinity. So what does that tell us? Well, that gives us enough information to solve this. It tells us the summation m equals 2 to infinity of 1 over n natural log of n diverges by the integral test. Okay. Questions on that one? Alright, with no questions, we'll move on to the next bit here. And so it's going to be the comparison test. Just like you had the comparison theorem for integrals, improper integrals, the comparison test is basically the equivalent to that. So we don't always have to look at the integrals, and there's ways to kind of fix these series so we can find a quick solution for ourselves. And I'll kind of give examples here. We have no other choice, right? So basically, if you have a larger series converging, then the other series, the smaller series, would converge. If you have a smaller series diverging, then the larger series would diverge as well. But so now, if you have a larger series diverging, that tells us nothing about the smaller series. So these are cases where you wouldn't have that information. And then the final scenario is if you have a smaller series converging, that tells you nothing about a larger series. So keep those in mind. We'll try and make sure we work these out in the appropriate ways. So our first summation, n equals 1 to infinity, 5 over 9 to the n plus 4. A good first choice would be to actually take a look at, can we integrate this thing? Can we integrate it quickly? And I don't know about you, but 5 over 9 to the n plus 4 does not look like a fun integral to me. Maybe it does to you, but to me it doesn't. So you can actually approach this a much quicker way. And so the main approach here is just basically to show what happens for the terms. So if you have 5 over 9 to the n plus 4, does anyone have a guess as to what we might want to compare it to? What series? Or what are the terms of the series in terms of what we should compare it to make this easier on ourselves? So I'll let you all take a guess. That's the main thing. Just try and get it out there. You're going to guess a few times. That's okay. It gets better in time the more you start playing with this stuff. So there's quite a few areas you can go with this. But so we want to try and have something involving n, but we want to either see, okay, is it going to be divergent? Then we want something that's going to be smaller. If it's convergent, we're going to want something to be larger. So where should we go with our other terms of the series? So this can be tricky in terms of what we're looking for. So we have some options, right? You have a 5, a 9 to the n, and a 4. If you don't see anything else, usually try and involve the n in some form. So we're going to have a 9 to the n involved. And if we can get rid of that 4, this does become a bit easier. If you compare this to 5 over 9 to the n, which one's bigger? So I saw the 1 over n squared. That's good. I just saw that pop up. So I like how we're dealing with the 1 over n squared, but notice what happens. So if I plug in 1 and I compare that, I get 1 here and I get 5/9 there, right? If I plug in 2, I get 1. Well, here, let's see. Actually, that might work just as well. So if I do 1 over n squared, so the first term I get 1 over 1, right? In the first term over here I get 5 over 9. So this would be greater at that point. The next term, 5 over 81 plus 4, so that's going to be 5 over 85. That's going to be 1 over 4, right? And then third term, this is 1/9. This is going to be 5 over, what do we have? I don't know what 9 cubed is. Well, I probably can figure it out. 729 plus another 4, 733. So this, once again, will be a little bit larger, right? Because we have something that's really vastly going to 0, right? So at the end of the day, what do we end up having? Well, I agree that that would work. So, but I don't think that's as obvious. We'd have to list out all the terms and figure out how fast one is decreasing over the other. So, but it does work in terms of the reason why is because you have, this is an exponential, and exponentials at some point overtake the other. This is just a polynomial down below. So you can get away with that. Now, the one I'd compare, to be honest with you, is something like that, because that's a little more obvious, right? Because if you look, you have 5 over 9 to the n. That's in direct correlation to what you have over there. The only difference is the plus 4. And anytime you add 4, that's going to make the denominator larger, meaning that is a smaller number overall. Does that make sense in terms of finding a comparison? 1 over n squared will work. It's just a lot harder to compare those two, and that I don't think is as obvious as the others. Does that make sense on that part? It's a great guess, though. 1 over n squared, those are the types of things we're looking for. That's awesome. So just usually we try and compare it to something that's a little bit closer to what it originally is. Are there questions on that piece? Because that is a tricky piece, and you can use other functions. It's just sometimes we want to make it so slightly adjusted that it's almost the same. So, but yeah, 1 over n squared will work. You get the job done. It's just going to be harder to always compare it to 1 over n to the whatever power. Okay. So yeah. So the exponential. So since it's an exponential, though, see how this is 2 numbers? That's the big thing with the homework problems. That's what I was trying to kind of tie in here. So now going from here, we have the summation n equals 1 to infinity of 5 over 9 to the n. Do you recognize this series at all? What type of series is it? These are tricky too. So I will say the 5 isn't going to make much of a difference. So this is equal to 5 times the summation n equals 1 to infinity, and then we'll have a 1 over . Yeah, so a power, we give this one a special name though. We just talked about it earlier in an earlier video. I had to kind of shut it down real quick to start the next video to try and get the screen captured. But so yeah, P series is close, and power series is something we're going to encounter later. So this one, maybe this might ring a bell if I write it this way. 9 times 9 to the n minus 1. Geometric, yeah, that's right. That's what we're looking for. So this is a geometric series. We can pull that 5/9 out in front. N equals 1 to infinity. And this is 1/9 to the n minus 1. Notice, so this thing right here, r equals 1/9. And so that's a convergent. Oh, and by the way, that's less than 1. That's why it converges. Convergent geometric series. Right? So that means that this thing converges by the comparison test. Okay. So I'm glad you mentioned the P series, because P series and geometric series are going to be our friends. We're going to use them over and over and over again. So keep that in mind. We're going to have to use P series. And a P series, just an FYI, that's something of the form summation n equals, it doesn't have to start at 1, but I'll put 1 just for kicks. 1 over n to the p. And so converges, this thing converges for p greater than 1. And the way you prove that is using the integral test once again. So you have those p series, we're going to make good use of them, right, a little bit later. So if you can always write it as 1 over n to the p, notice our variable n appears as the base, and the exponent is just some constant p, essentially, is what that's saying. Okay, but if it's that p is greater than 1, you're done right away. So great job on tossing in p series and all that. So how is that different than 5/9 raised to the n? Notice your I'll put it in blue here. There's your variable here. Notice it's up in the exponent. Notice here is your variable down as the base. No, and so I know you're not trying to be silly. Yeah, it's really a great question. So P, what that's telling you, it's telling you, for example, if I give you summation n equals 1 to infinity, these are natural questions that you're having, and that's exactly what I want to see. So summation n equals 1 to infinity of 1 over n squared. You can say this is a convergent p-series. With p equals 2. If you change that to, so now I can try another one, right? So if I change this to n equals, pick your favorite 3-digit number, toss it down there, and I'll show you how this whole argument changes. So I don't care who tosses, just give me a 3-digit number, whatever sounds like your favorite. If you want to really challenge me, you can give me a 4-digit or a 5-digit number. Okay, 216, very good. So watch this. I go summation n equals 1 to infinity of 1 over n to the 216. It's still a convergent p-series with p equals 216. Right? It didn't really matter what number he gave me as long as it's bigger than 1. So as soon as I said 3 digits, we're done right there. Okay? And in fact, it doesn't even have to be an integer, right? If I chose p to be pi, the summation n equals 1 to infinity of 1 over n to the pi, that actually, even as crazy as that might sound, that's a convergent p-series with p equals pi, right? So that's really some of the crazy stuff that happens with these series, but all we need is it to be greater than 1. On the flip side, if p is less than 1 or equal to 1, we have it diverges right away. So you can also have those cases where it diverges. So beautiful results on both sides of the fence there. So yeah, so p is just the power that your variable is raised to. So notice our variable in those cases are in the base. So you have, see how the n's down below. That's actually extremely important in terms of how we go about tackling these problems. So great questions. Those are awesome. Those are the types of things I look forward to hearing. Usually you get them in a face-to-face class too, so it's quite natural to ask those questions. So does that make sense on the p-series then? If not, that's going to be our backbone. The p-series are what we use over and over and over again for comparison. So awesome. I'm glad to see that works. So now our next one, what we're looking at, 1 over n minus 2. But notice n is greater than, or n is equal to 3. So we have 1 over n minus 2. What's a natural comparison in this one? What would you want to compare it to? What seems very simple to compare this one to? So we'll see if you're getting the hang of it. Big thing, just toss stuff out there and we'll see what happens. One over n, awesome sauce. Yeah, that's exactly right. That's exactly what you're going to compare it to. And so when n is greater than or equal to 3, you can plug them in and see real quick. I mean, so if we plug in 3, you get 1 on the left-hand side, you get 1/3 on the right-hand side. So this thing is always going to be greater for n greater than 3. So this thing's always defined, n greater than or equal to 3. So notice the summation, n equals 1 to infinity of 1 over n. Hey, that's a p-series, right? Oh yeah, there is a bit of a delay. And actually, so there's a delay when I speak, actually, before you get to hear the clip. So what you're hearing right now is probably a 40-second delay or so. So it just takes time. That's why I got to give you time. There's always some lag time between the video and the time you actually see it. So, but just be patient. I promise I'll listen and see what your questions are, and I'll answer them. So something I've learned to do is just wait around. So now, the summation n equals 1 to infinity 1 over n, you can say it's a p-series. It's actually so special in terms of, usually it's the first example people see of a divergent series. And it's so special, it's given a special name. This is a divergent, you don't have to write the word divergent, but that's what we're trying to prove, so I want to get it out there. Harmonic series. The only reason it's called harmonic is because p equals 1. You can't say it for any other value, but it's just a special one. You're going to want to learn it. We will use it when we talk about absolute convergence and conditional convergence. It's going to come into play again as your standard example. So this is divergent. So we have a smaller series that's divergent, and so that means this original summation is divergent by the comparison test. Okay, so so it's I'll be honest with you, I used to know it at one point in time. I'm not exactly sure why it's called the harmonic series, but I could find an answer for you. It doesn't take me too long. I won't do it right now, but I'll try and get an answer to you. Just shoot me an email as a reminder. That'd be great, and I can get you an answer as to why it's called the divergent harmonic series. There's a few reasons involved, and I know how the proof of this works. I mean, basically you're looking at these partial sums. So for example, you could say S1 equals 1 over 1, which is 1. I'm referring to this one. And then S2 equals 1 plus 1 half. And then S3 equals 1 plus, or let me look at this one actually. S4 equals 1 plus 1 half plus 1/3 plus 1/4, which is greater than 1 plus 1 half plus 1/4 plus 1/4, right? So what's happening now? So notice if I take this, I get 1, I get 1.5, I get, what is this value going to be? Well, if I go 1 plus 1 half plus 1/4 plus 1/4, rather than looking at the 1/3, I get another 1 half. So 1 plus 1 half plus another 1 half. Well, that's going to equal 2. And so you actually continue this process. The next one you look at is S8. You'll get 2.5. Then you'll get S16, and it will be 3. S32 will be 3.5, so on and so forth. And basically you found something that's increasing by 1 half for some terms of these sequences. And so all of a sudden this thing can't converge. It must diverge, right? There's going to be some crazy stuff coming up. So the idea of conditional convergence, so the way we say it is, okay, does the absolute value converge? We call that absolute value convergence, absolute convergence. If we just look at the regular series of an alternating series, that might converge by itself. But this conditional convergence idea basically allows us to rearrange the series, how we write the terms, and it can converge to different numbers, which is really weird. But we have we'll see some of that stuff later on down the road. So there's really some cool things that happen here. But yeah, I'll get you the history on the name. Just shoot me an email, give me a reminder. Be happy to do it. So okay, so moving forward on this part, let me get that out of there. So, oh yeah, I guess I don't need to. Yeah, we'll just move forward to the next page. So limit comparison test. Basically, you can take that idea of comparison test, but it's a little bit easier. Rather than having to find something greater than or less than all the time and be very stuck on that, we can cut down the time drastically by just taking a limit of some similar sequence. So, and we want to always make it a similar sequence that we know what the heck it looks like, right? If you look at this one, this looks all sorts of crazy. Now, P-series stuff we know, and that's something I'd recommend in this case. When you take a look at this one, what actually happens? Well, you can look and kind of break this thing on down. Just look at the powers. We have a k to the first and a k squared. So that essentially makes a k cubed up top. And down below you have a k and then a k squared and squared. So that makes k to the fourth and a k to the fifth. So my claim, I'm not saying this might be the most accurate, but I'm going to claim that this is going to behave something similar to 1 over k squared. And notice all that I did is I didn't really worry about all these constants, all this other junk mixed in there. I looked for the highest degree in both the numerator and the denominator. And I'm saying that this series is probably going to behave like 1 over k squared. So now the real thing I'll look at, and so as I mentioned, we know that this summation k equals 1 to infinity of 1 over k squared is a convergent p-series with p equals 2. Okay? So now, moving forward from here, what the heck do we do, right? Well, we got to take the limit of all this junk. So this looks all sorts of crazy, but we'll see if we can fix the crazy here. So we want to do limit, instead of n going to infinity, we're using k, so we'll do k going to infinity. So we get an, well, this is our an, this whole bit, and this would be our bn. Okay? So we have 2k minus 1, k squared minus 1, all over k plus 1, k squared plus 4, the quantity squared. Oh, I should say one extra caveat. I didn't check for one thing, and I hope we can see it though right away. What was the one piece that I needed to check first? It's kind of a taken for granted in this, so but I need to be careful a little bit with this. If you notice on the terms, every term has to be positive, right? If I don't have positive terms, all bets are off, right? So, but that's not too bad. When you plug in 1, you'll see right away you get 0 for the first term, but then 2 and so on and so forth, they're all going to be positive right away, so no reason to worry there. So the limit as k goes to infinity. Notice we have 1 over k squared in the denominator. That means you can kick that k squared back on up, right? So we can rewrite this as the limit as k goes to infinity. Now here's the fun part. Let's break this into something that's very simple for ourselves. So we can break this up into separate limits just by, all I'm going to do is algebra. So this is 2k minus 1 over k plus 1. I'll break it up into another limit as k approaches infinity. Notice how you have the k squared plus 4, the quantity squared. So let's break it up into k squared minus 1 over k squared plus 4. And then you have the limit as k approaches infinity. And then we'll have k squared over k squared plus 4. So now, I'll kind of mention how we can approach it. If you want to see the extra steps, I'm happy to do it. But here's the beauty of Calc 2. If you're good with limits, this whole thing, we start to cut down time drastically. I don't need to see every single step. Notice you have L'Hopital's rule. You can do that like crazy if you want. Yeah, at the end of the day, we can get through these pretty quick. Okay, so in this one, notice the first limit. You can use L'Hopital's rule because you have infinity over infinity, so you get just 2 over 1, which is just 2. Second case, you can use L'Hopital's rule twice. You'll get 1 as that limit. And then the third case, you'll get 1 as that limit as well using L'Hopital's rule twice. So the whole answer is 2. So what does that mean? Well, that means the summation k equals 1 to infinity. Oh, guess I got to write out all that junk again. 2k minus 1, k squared minus 1, all over, what do we have, k plus 1, k squared plus 4, the quantity squared, converges by the limit comparison test. Okay. Questions on that one? All right. So now, with this next one, it's starting to get a little bit trickier on the next one. So, does anyone have any ideas as to what we might want to try on this one? box that off. And by the way, when you're looking at this, it's not the integral test, and the reason why, that's going to be a nasty integral. Same thing with the one up above. Those integrals are just crazy hard. So what was this? You can't just look at the first half. Okay, and I agree. That's exactly what we want to try and do, is simplify it into something that looks like the first half. Now you might say, maybe we can use a comparison test, right? But so let's kind of look at that. If I compare n e to the n to n e to the n plus 1, right, which one's larger? Well, it's going to be obvious on that side. Okay, so that means if I flip it, 1 over n e to the n, I flip this. Right? Hopefully we buy that thus far. Okay, now where do we go from there? Well, okay, so if we do e to the n on top on the one side, we're good. We have to do it to both sides, right? But here's the big caveat. Where am I adding the 1? Well, it's over on the right hand side on the smaller piece. So anytime you're adding in that numerator and you're looking for it on the other side, we're running into a little bit of trouble there. So I'm not saying, actually, I mean, you can toss it out after the first term, but at the end of the day, it might benefit us rather than trying to set it up when we're adding the extra number in the numerator over on the right hand side. It's not going to be quite as perfect in terms of what we're looking for. So that's why we probably just go with a limit comparison test. And yeah, if that is the case, you can kind of see, you said, hey, just drop the 1s, and I agree. You have e to the n over n e to the n, and that just leaves us, the e to the n's would cancel. The big to do would be n equals 1 to infinity of 1 over n. And so this is a divergent harmonic series. Okay. So the limit as n goes to infinity of this thing, so we have e to the n plus 1 over n e to the n plus 1 all over 1 over n. Notice that thing equals the limit as n goes to infinity. This means the n would come up top, right? So we have n e to the n plus 1. And then you're having an n e to the n and then the plus 1 there. Now you can use L'Hopital's rule. So L hop, that thing. So you get limit as n goes to infinity of what? Well, L'Hopital's rule would say, and we had infinity over infinity. It's not always the best case to use that, but we're in decent shape here. We'll be just fine. So you get e to the n plus 1 plus n e to the n. And then in the second, on the bottom, you'll get e to the n plus n e to the n. Right? You might say, oh, Josh, this is getting all sorts of nasty now. Well, not really. The 1 will go away, and then we have pretty much everything matching up. So the limit as n goes to infinity on our next one, we get e to the n up top, the 1 goes away, and then we'll have plus an e to the n plus n e to the n, And the same thing down below, e to the n plus e to the n plus n e to the n. And so notice that whole thing equals 1 because all of it cancels. Okay? So that means, at the end of the day, what do we have? Well, it means we have the summation n equals 1 to infinity e to the n plus 1, and hopefully this will fit on the screen. And e to the n plus 1, it diverges. By the limit comparison test. Fun result right there for us to see. Okay, questions on that? So good find on saying that, hey, this should behave like just the terms without the ones. That's exactly what we're looking for. Just take out the complicated stuff and you're in good shape. So now the next component that we're going to do, the next test that you kind of look at, you have an alternating series test. Notice this alternating series, there's two parts. First off, the first part, bm plus 1 is less than or equal to bn. What does that say? It says it's decreasing. Okay, and it says the limit as n goes to infinity of b sub n, just the positive portions, is equal to 0. So you have decreasing and then that equals 0. Then the series is convergent. This is a big to do because a lot of people make the mistake. This says nothing. So here's a comment. Alternating series test. Will not tell us about divergence. It can only tell us about convergence. If you want to show that it's divergent, you go back to what's called the test for divergence, because basically you have the limit as n goes to infinity of b sub n being something different than 0. That tells you it's going to be divergent. Or if you have something oscillating, that means you're not going to have oscillating in the positive numbers, I should say, then you're not going to have a limit as well. So you have other cases like that too. So hopefully that makes sense. We're going to be looking, is it convergent? If not, we're going to use a different test. All right. So our first one, remember we got to show it's decreasing, and then we got to show the limit as n goes to infinity equaling 0. The easiest part on all these, I'd say, is the fact of showing that the limit either equals 0 or does not equal 0. So that's what we'll do right away on this one. Limit as n goes to infinity. So what is b sub n here? Well, b sub n equals, basically take away that part. So you get b sub n equals n squared over n cubed plus 4. Okay, so our limit as n goes to infinity of n squared over n cubed plus 4. Well, that should be the same thing as limit as n goes to infinity of 2n over 3n squared. Notice the n's will cancel, and then you're left with just limit as n goes to infinity of 2 over 3n. You didn't need to show all these steps. We have it equal 0. Okay? So what happens? We have that. Does it mean this thing is convergent? No. We need to show it's decreasing. So what we'll do is we'll let f of x equal the function x squared over x cubed plus 4. Then what happens? Well, let's look at f prime of x. So notice that becomes x cubed plus 4, the quantity squared. Up top we'll have to take the derivative, so we get a 2x times x cubed plus 4 minus, it goes x squared, and the derivative of the denominator is just 3x squared. So this whole derivative became, what do we have here? We get x cubed plus 4, the quantity squared. So now we'll have a 2x to the 4th minus a 3x to the 4th. That's going to be negative x to the 4th, and then plus 8x, right? And you might be saying, well, whoa, wait a minute. this thing isn't decreasing, right, all the time. Because when x equals 1, notice we have a positive 7. And you can actually solve this thing, to be honest with you. So if you go, we can write this as negative x cubed plus 8 times x all over x cubed plus 4, the quantity squared. Notice we're squaring the denominator, so that's not going to make much of a difference. And so if we try to work this out all the way, you're going to have when x equals 2 is when the numerator is equal to 0. So anything below that's positive, and anything below that's, or going beyond that, is negative. So this means f of x is decreasing on the interval 2 to infinity, right? Well, if that's the case, we're in pretty good shape. Oh, I should put, I don't want to include 2, I want to have 2 to infinity. But so notice their first two terms may not be decreasing, but after that, yeah, it's going pretty good, and everything's decreasing from there on out. So this still suffices for us to pass the alternating series test. So the summation m equals 1 to infinity, negative 1 to the n plus 1, n squared, and then we have a n cubed plus 4 is a convergent alternating series. Since it passes the alternating series test. Hopefully that makes sense on that one. If not, let me know. Next one, limit as n goes to infinity. And by the way, we have b sub n equals sine of pi over n. Limit as n goes to infinity of sine of pi over n equals the sine of the limit as n goes to infinity of pi over n, which equals sine of 0, which in fact equals just 0. So we're in good shape there. And moving forward, what do we see? Well, we can compare it actually if you wanted to do a bn and bn plus 1. But if you wanted to, we can let f of x equals sine of pi over x. Then that means f prime of x, this is going to be an easier derivative for us. What do we get? Well, we'll get cosine of pi over x times, notice this is pi times 1 over x, so this is pi times negative 1 over x squared, which is the same thing as negative pi cosine of pi over x, and all that's over x squared. Let's think about this, okay? There's your unit circle. 0, here's pi over 2, and here's pi. Notice x, the x values on this thing is cosine theta, the y values are sine of theta. So when you're looking at this, the first value would be when we plug in 1, notice you get cosine of pi. So you start here, and notice your x value would be negative 1. Then your x value gets to be 0. Right, when x equals pi over 2. So actually this derivative, once again, we have x, we have f prime of x, and we have 2 as our magical value where this thing gets 0. Okay? Unit circle's the next tattoo. Well, I guess if you get it as a tattoo, I'll definitely let that happen on the test. So that's for certain. Yeah, unit circle comes all over the place. Yeah, if you want some identities and you want to tattoo them, go for it. So yeah, in terms of what goes here now, let's see here. I'll change the color real quick. So now notice our first value is anything less than 2, that's going to be positive because we have a negative and a negative, that makes it positive. but anything 2 and beyond, we're going to be all within this quadrant right here. So all the x values are positive in there, so we're good to go. Now, keeping that in mind, what happens? So this is decreasing on the interval 2 to infinity. That was just kind of a happy little coincidence there too, by the way. It doesn't always happen where it's 2 to infinity on all these. So you get -1 to the n sine of pi over n converges by the alternating series test. Okay. Now the last one, this is going to be a doozy. So you're not going to use L'Hopital's rule or anything like that to take your limits or have anything real nice that you can use. In terms of the limits, oh, does everyone have what's up above? I want to make sure. I'm going to need some room on this one. Just to make sure it fits on the screen. So I'm going to erase all this. And we'll write number 3 right up top. So part of my screen is actually cut off, and that's the reason I gotta start to write this. And hopefully by the next live session I'll have everything fixed. So, all right, let's take a look at this thing. If we note b sub n equals square root of n plus 1 minus the square root of n, f of x equals square root of x plus 1 minus the square root of x. So we'll kind of get into the next bit in a second. First thing, limit as m goes to infinity of square root of n plus 1 minus square root of n. Notice that's infinity minus infinity. Any ideas how we go about this one? This is kind of tricky, so you can't, and I'll give you a hint, you can't use L'Hopital's rule. That's out. So what the heck do we use in that case, right? No idea. Yeah, that happens pretty often. Actually, on a side note, this was a question, something similar to this, in a Math Jeopardy competition for Mathematical Society. So these aren't always the easiest, but they're done in a similar approach. So when you have subtractions of square roots, there's something to kind of take note of. If I want to get rid of the square root, and the only way you can do that is to do what's called completing the square. You have an a minus b. This is what you have right here. If you multiply both sides by a plus b, but you got to do it in a special way, which I'll show you here, you get a squared minus b squared. Okay. So what we're going to do is we're going to multiply by a fraction. We'll multiply by the fraction square root of n plus 1 plus square root of n. We can't just do that willy-nilly, so the way to fix that is we put the same thing in the denominator, and that fixes it for us. Okay. So notice what we do is we now have, this is our a plus b, or sorry, a minus b, and this piece is our a plus b, right? So at the end of the day we have a squared plus b squared, so you have a squared is n plus 1, right, is what we're left with. When you take a square root and square it, you get n plus 1. Then minus, right, because we got to subtract off b squared, so that would just be n. And then down below, we're just going to have square root of n plus 1 plus square root of n. And I forgot to write that limit. Sorry about that. Limit as n goes to infinity. Okay, so moving forward from here, what do we get? Well, this thing equals the limit as n goes to infinity. Well, the top just simplifies to 1. Right? And the denominators go to square root of n plus 1 plus the square root of n. Well, notice we have two n pieces in the denominator, so this whole thing equals 0. Okay? So hopefully that makes sense on that part. If not, let me know. That's called conjugation. We're multiplying by the conjugate is all that we're doing there. So the next piece, so we have that part done, we got to look at the derivative. So f prime of x equals, so derivative of this first part, you're going to get 1 over 2 times the square root of x plus 1 minus 1 over 2 times the square root of x. If the derivatives don't make sense, let me know. I'll be happy to show you. Basically, I just wrote those as x plus 1 raised to the 1/2, and then an x to the 1/2, and then just kind of use power rule. Now from there, I need to get a common denominator. So in order to do that, I need a square root of x in the first term. So I'll put a square root of x down below, but that means I put a square root of x up top. And in the second case, I need a square root of x plus 1. So I need that, and I get that down below and up top. Okay. So what does that mean? Well, it means our derivative equals the square root of x minus the square root of x plus 1, which is always going to be larger than the square root of x, all over 2 times the square root of x plus 1 and square root of x. And notice this thing, for all x greater than or equal to 1, this thing's always decreasing. So this tells us f of x is decreasing. We can even include 1 and go to infinity. Okay, so that tells us about the sum. Sum n equals 1 to infinity of negative 1 to the n square root of n plus 1 minus the square root of n converges by the alternating series test. So notice all the alternating series test does, if we're using it. Now that doesn't mean that all the things with the summation n equals, or where we have 1 to infinity of negative 1 to the n of some other piece there always converges, right? You got to be careful there. If you want a quick example, I'll give you another. So for example, if I do sum n equals 1 to infinity of, let's say, negative 1 to the n plus 1 arctangent of n. Okay, so if I take a look at b sub n equals arctangent of n, that means when we look at the limit as n goes to infinity of arctangent of n, now you may or may not remember this one. So first off, I'll draw a tangent. That's pi over 2, that's negative pi over 2. And you repeat this, but this is y equals tangent of x. So that means you kind of reverse the roles of x and y. And so now this is negative pi over 2, and this is pi over 2. And this is y equals arctangent of x. Okay. So the limit as n goes to infinity of this, well, notice as we were approaching infinity, this thing approaches pi over 2. So now, what's the reason for this to diverge? Well, it's actually not the alternating series test. If you're using the right terminology, we have a thing that's called the test for divergence. and that says if it's not equal to 0 by the test for divergence. If it's not equal to 0, then this thing automatically diverges. It's all done right away. Just wanted to make sure you saw that. So do you all have any more questions on this? I know the series stuff gets really tricky, and if you do, don't be afraid. If you forget and you want to ask one later, or if you want to get into ratio and root tests and things like that, I can get into those a little bit later, along with absolute convergence and conditional convergence later on this week. But are there any more questions on any of the alternating series tests, comparison tests, limit comparison test, what else do we have? Integral test or geometric series? So if there are, please ask them now. Yeah, so like to do some more reviews. Yeah, so that shouldn't be a problem as long as you want to do reviews. Everything's back up and running. I just had to have the computer re-imaged, and we changed our emails and stuff. So yeah, I'm happy to do more and more of these, and if you need more time to digest it, don't worry, the videos will be up there. Yeah, so just keep on asking questions in the meantime, and put them in the discussion boards, and I'll try and take them into these review sessions. So I'll plan on doing one later this week as well, possibly Friday-ish, Friday, Saturday, something like that. So keep that in mind. I'll definitely send you out an update, and hope to see you all in that next review session. And don't be afraid, I'll be in my office on Wednesday and Friday as well, so you're more than welcome to stop by. Yeah, so you're more than welcome to stop by my department, and if you have questions too. So doesn't have to be just the review sessions, but you can come by as well. But either or, I'll be hosting a lot more review sessions. So hope you all have a good night, and I will see you next time.